Hello, everybody. Hopefully you're where you want to be. So this is the AMReX session. So people always ask, how do you pronounce it? And I say, well, we call it AMReX, but it's OK if you call it AMReX. So this is the block-structured AMR software framework. And again, we have an issue. Is it a framework? Is it a library? You can decide at the end. The focus of this is in some sense going to be on AMR, which is adaptive mesh refinement. But one of the things that I want to point out is this is a framework for anything that you want to do that is structured. So the real difference between this session and the session across the hall is everything that we're going to talk about in this session uses a structured mesh. Okay, we'll talk about why we do that. But that is the key difference. So people say, well, can I do blank with AMReX? And the answer is, if your mesh is structured, then yes. If you're doing unstructured stuff, then go across the hall. So that's sort of the kind of, other than that, there's a whole lot of things. And there's a caveat, which actually we have a number of applications that are particle only, which are inherently unstructured. So when I say structured only, if you have a mesh, it needs to be structured. You can also do particle. OK, we're going to have a hands-on component. Oh, I forgot to. So I'm Ann Almgren. I am the deputy director of the AMReX Co-Design Center, which is part of the ECP project. I'm also the applied math department head at Lawrence Berkeley Lab. Erik has been a member of the AMReX development team and has recently taken a job as a NERSC software integration engineer. So if you have any job type questions about like, hey, I'm thinking about working at NERSC, ask Erik. OK, we're going to come back to the setup, or should we do it now? OK, so Erik, take it away.
OK, I think it's going to work best like this. Sorry. OK, let's just
quickly, we do have change.
OK. So if you're following the slides, I'm going to be following the directions on the slides. Is this going to cause complete disaster?
Oh, it's thinking.
It's thinking, OK. And then it's giving me a separate screen. So I do not want a separate screen. I want the same thing. OK.
There it goes.
And I should have.
There we go.
All right, so this will be my first. Could have done this better moment. And what I want to do is, should I just do it later?
We'll do it later. OK.
OK, let's do it later. Sorry.
We actually do practice this. It just never quite works out. So what we're going to do is I'm going to talk at you for a little while. Then we're going to do a hands-on. Then I'm going to talk at you a little bit more. We're going to do a hands-on. That should work out about right. What we're going to be doing is having everybody log onto Theta. We've got preloaded executables there that you'll be able to copy into your space. You'll be able to run them, look at things like scaling, some visualization. The hands-on part's always a little dicey because sometimes things work and sometimes things don't. So everything that you would do hands-on is also available on the website. So if you'd rather, when Erik goes through the presentation, if you want to kind of follow along, that's fine. That would be a demo, or you can do a hands-on. OK, coming back. Oh, did you plug me back in there? OK. So setting the stage. Some of you are computer scientists. Some of you are domain scientists. I call myself a computational scientist, which I'd say I live in this world in between the two. So I don't spend time thinking about MPI or OpenMP or exactly how the guts of these things work. But I'm also not a biologist or an astrophysicist or a chemist. So I'm somewhere in this space. And in this space, the perspective, what I see is we've kind of solved the easy problems. So the problems that we're going after now are hard. And that's why we have sessions like today, is because you need to bring all the tools you can to bear. And just kind of cutting to the moral of the story, you're actually never going to be an expert in everything that you need to do a really kick-ass simulation. Okay? You're just not going to be the expert in MPI and CUDA and biology or astrophysics or whatever. You're not going to be. So the question is, where do you want to be the expert? So this is the piece of the problem that we represent. So coming back to it, the problems today are hard. Okay, what do we mean by hard? They are often multi, as we say. So they couple multiple physical processes. They are across a range of spatial and temporal scales. So they're multi-scale, multi-physics. People talk about multi-rate, which usually means time. So they're multi. Gone are the days of simple physics, simple geometries, single algorithms. We don't just do one thing a lot of the time. Or homogeneous architectures. And that's really the one that's bitten us in the last, let's say, 5 to 10 years, is it used to be you wrote it for CPU. And so we started doing the software stuff in the days before parallel was a thing. And honest to God, when somebody said parallel, I said, that'll be a fad. They'll just keep making bigger shared memory machines. Then we got to parallel, and if people remember, there was vectorization, then came parallel, and vectorization went away, then vectorization kind of came back, and then, oh my God, we have these GPUs, and when ECP started, a bunch of us were just making this up. Yeah, we're gonna run on GPUs because we're gonna ... Here we now are. We all run on GPUs now. Okay, that is just the norm. You can't dodge it because that's where the allocations are going to be. If you want to run on a supercomputer, they're going to have GPUs. You say you want to run on a CPU, you're low priority. So the reality is you're going to run on GPUs. How are you going to get there? Okay, so the other thing is how do we build these algorithms and software for these hard multi problems without starting over every time? Because I don't want to do one application my entire life. I don't want to run on one machine my entire life. So I need to be able to switch gears to do new things. I don't want to start over. I don't want to say, oh, there's this new problem. In 3 years, I'll be able to contribute. Okay. So again, I said that this is a structured mesh session. Not all simulations use a mesh. So I want to kind of step back. I know that one of the criticisms of ATPESC in the past years have been we all do sales pitches. We all think our software is wonderful. So this is the step back and say, you know what, there are a lot of simulations that don't use meshes. And so molecular dynamics is a classic. I've gratuitously stolen images off the internet and things here. If you are a domain scientist or somebody new to computational science and you're thinking about an application, one of the first questions you usually have to figure out is how are you going to discretize space? Okay, because a lot of problems have spatial components, right? We do fluid flow, we do electromagnetics, we do cosmology, astrophysics, traffic flow, epidemiology models. These things have an element of space, right? Even in an epidemiology model, which might be agent-based, the agents are moving. You have to somehow discretize space. And so your main question is usually first, structured or unstructured. There are pros and cons. And the other sort of takeaway message in this is everything's a trade-off, right? Some things are better for some reasons at some times. Other things are better. It's not a something always wins. So trade-offs. Why do you like structured? Why do I like structured? I like structured because it's a whole lot easier to write discretizations. If I want to write down a derivative in the x direction, I say, well, it's phi at I plus 1 minus phi of I. It's structured, so I know that I plus 1 lies to the right of I. Okay, that's good. What that means in terms of computation is you have simple data access patterns. So if you have multi-D arrays, you can write out your data in a way that when you go from I to I plus 1 to I plus 2, your data is contiguous. This gives you good access patterns. We'll talk in a minute about the extra order of accuracy. The other thing is a lot of times people think, well, if it's structured mesh, I can't do any kind of geometry. That's not true. You can do some kinds of geometry. You can't do some kinds as well as unstructured mesh. But the trade-off is there are ways of generating, and when I say geometry, I mean bounding regions, like I want to do flow inside a cylinder instead of flow inside a box. Maybe I want to do flow around a sphere. That's what I mean by geometry. We spend our time worrying about how to discretize the flow around that object rather than generating the mesh. So what you hear a lot about in the unstructured world is generating the mesh, right? There's a huge amount of time in how do you generate the mesh? How do you make sure the mesh elements have the right ratios? How do you make a good mesh? We say, oh, that's easy. I write down a bunch of lines, right? We'll show you some pictures. Okay, unstructured has a lot of great qualities. Okay, so one of the biggest ones is you can fit the mesh to your geometry. And if you're doing boundary layer flow over an airfoil, you really would like to fit that mesh to the geometry. The way that I would propose to do it for other things doesn't work well for that. You don't have a loss of accuracy at domain boundaries. That's because you're working so hard already to deal with these irregular elements. The elements at the mesh boundaries are not more irregular than the others. You have a lot of bookkeeping. So I was talking about I plus 1. I think in terms of like Fortran arrays, which actually in C++ we make them look like Fortran. But what's the relationship of the value at I plus 1 comma j to the value at ij? Well, in an unstructured mesh, I can't have just ij because I don't have rectilinear. Okay, so then we talked about the geometry generation. All right, again, when people think of structured grid, they usually think of this upper left, right? That's a grid. And that is your starting grid. That's where we like to start. But then you realize there are a lot of things that you can do with that, right? Structured mesh is really about the connectivity. It's really about knowing who my neighbors are. If I'm going to do a flux calculation, I want to know which faces are how do I label the faces between cells? So here the key is that logically rectangular, which is logically is in the ij space, does not necessarily mean physically rectangular. So again, I did some gratuitous grabbing of pictures off the internet. structured with non-constant cells. So what I mean there is that delta x in one place does not necessarily equal delta x somewhere else. Kind of split the pros and cons. So you have the structure, you have this known connectivity, and you can fit some geometries. So here's one way of doing mesh refinement, is where you say I'm going to have a fixed number of lines, I'm going to squeeze them together. This works really well for some, well, it works okay for some types of problems, it doesn't work at all for other types. In the middle you have bathymetry, right? So there again, you might have, oh, that's 32 by 64. It's a structured mesh, delta x and delta y, or in this case just delta y, are changing dramatically. That might work really well if the region that you want the higher resolution is that region to the upper left. But you're kind of locked in there. If you decide it's structured that way, that better be where you want it. You can also do things like curve the meshes. So the takeaway from that is logically rectangular doesn't mean physically rectangular. And again, one other generalization is people say, well, I'm not doing flow in a box, right? I have all this empty space. This is an example. This is a very simple prototype of a chemical looping reactor. And as you can see, there's very fine pipes around the outside, a lot of space. I don't need to resolve that space. Nothing's happening there. These are pipes or cylinders, actually, you can't see. So again, structured grid doesn't mean, oh my gosh, I've got to deal with this whole rectangle. I'm going to waste all my space in the middle. You can play games. We call this mesh pruning. We kind of made that up. So you can get rid of meshing in the middle. In this case, what you see as the squares, those are not individual cells. Those are boxes. So those might be like a 32 cubed. OK, so the idea, the takeaway here is structured mesh doesn't have to mean just flow in a box. OK, there are games that you can play. You can have metric terms so that you can fit these to other geometries. And you can also do things like this. OK, so I made a comment about constant cell size, right? So unstructured mesh doesn't have it. Also, the examples that I showed you, they're structured, but they don't have constant cell size. Why do I care? OK, so I don't know how many of you took a class in numerical analysis, but there is some version of this in every numerical analysis class. OK, so if you want to ask what is the order of your approximation, here I'm not even solving an equation. I'm just trying to represent a derivative. And the easiest thing to do is a centered difference. That's kind of the number one thing you learn. And so you have a phi at I plus 1 and a phi at I minus 1. So you have an x sub I, and there's to the right and there's to the left. And I want to take a centered difference. And I can write out a Taylor series. Okay? So I have some phi, and there's a phi x is the x derivative, phi xx is the second derivative. I can write those out, and I can write down a first order derivative, phi I plus 1 minus I minus 1. And typically we would have a 2 delta x there, but here my delta x is changing. So this is an approximation for phi x. That's what I wanted. It's a first derivative. What is this next term? If delta x is constant, that next term is 0. And so you can see I've got an order delta x squared. What that means is I've got a second order approximation here. Okay? So that term, if I refine my mesh by a factor of 2, I get 4 times better accuracy. The reason that we make a big deal about this whether it's a constant cell spacing is because of this middle term, the one that's in red there. So if that's not 0, my approximation, I've lost an order of accuracy. Now, in practice, what people do is if you change the mesh relatively slowly, yes, it's technically first order, but that's very, very small. So I don't want to say that methods that don't have constant dx never work. This is why we care, though. Okay, this is why we care. This is just a first derivative. You can imagine higher order stencils. You're going to lose accuracy if your mesh spacing changes too dramatically. You will have to use much larger stencils, which start to have issues in other ways. So if you can make delta x equal delta x right and left be the same, you kind of got something for free here. So the problem is, as anyone who's done this knows, if you want to zoom in somewhere, you want really fine detail somewhere else, you actually just plain can't afford to run something with that resolution everywhere. You can't afford it because it might not actually fit on the machine. Literally, we're talking about problems that don't fit on today's supercomputers. It's also the case that even if it did fit, you can't get an allocation big enough to run that problem. So basically, everybody who's doing this today is using some kind of refinement. In unstructured grid, it's a natural thing because you can do whatever you want with the grid. If you say, well, I want a structured grid code for all those benefits, I've just sold you that this is great. I want delta x constant, but I can't afford uniform resolution everywhere. That's how you come to AMR. And this is what we call block-structured AMR, which means we are not refining on a cell-by-cell basis. We're refining blocks. Okay. So what does this do for us? And here are 2 different pictures. There are 2 different sort of styles of block-structured AMR. We actually have fun arguments about which one is Should we call this one patch-based and that one's block-based? Anyway, what's the point of AMR? So mesh refinement obviously means there are places where the mesh is finer than other places. Adaptive means you allow it to change in time. Adaptive doesn't have to be changing in time. You can have fixed. You want to refine in a region of interest. You, in the way that we do this, you as the user decide what your region of interest is. In flows, in fluid flows, we often say it's the vorticity. It might be the magnitude of a scale. If you're following some reaction, through a flow, you want to know where is that tracer, where is that contaminant, if you're doing that sort of thing. So you refine it. Okay, that's good. I'm saving on cost here. The second thing is I allow local regularity. When I'm doing operations within one of those boxes, now here, each little black box is a cell, so you can see that when I go from black to blue, it's a factor of 2 refinement. When I go from blue to red, it's a factor of 2 refinement. So this would be a very small problem. So within each box, it looks just like a regular grid. You don't know that there's mesh refinement. You're just doing an operation on a nice structured grid, constant delta x. So you've got that accuracy we just talked about. You've got that ease of discretization, and you've got that data access pattern. The other thing it does is now we have this set of boxes that we're dealing with. And they live at different levels. And when we say a level, we mean what the mesh resolution is. There is a natural way to do hierarchical parallelism here. So you have loops over levels and over boxes, and then for each box, you have a loop over cells. So before the GPU days, one of the things this made really easy was MPI plus OpenMP. Because we do MPI over grids, OpenMP over boxes. It was a very natural way to do parallelism. Same thing today. MPI over grids, which means here, well, I've only got one grid at level 0 there, but I've got 2 blue grids at level 1. If I have 2 MPI ranks, each one can be working on a grid at the same time. So MPI over grids, but now I can send an entire box of data to one of the GPUs, so I'm using the GPU threading over that grid. So it's a very natural paradigm. It's a really easy way to break it up. If it's single level, we just call it domain decomposition. If it's multi-level, we call it mesh refinement. Okay. I've made it sound like everything is perfect. There's the problem with these interfaces, right? What happens at the coarse-fine interfaces, that is the hard part. But what you've done is, in some sense, you've localized the hard part. So you have to do special stencils there because you have this change in delta x, which means you have to do something, a bigger stencil if you want to maintain your order of accuracy. But you know that you're only doing it at these boundaries. So you're not sort of, I think of it as contaminated. It's not fair. You're not messing up the solution everywhere. You're only messing it up at the boundaries, but at the boundaries, you know how to fix it. So that's kind of that trade-off. And then, so special discretizations only at the interfaces. And again, in terms of bookkeeping, especially if you use a global index space, which is the way to go, then it's very easy to say, this coarse cell is next to this fine cell. I've got a global index space. I know the ratio. OK, those are the things that are in common for all these block-structured mesh applications. Different styles. I have an AMReX grid on the left, a flash grid on the right. These are called quad-tree or oct-tree grids. We used to claim that these were block-structured. Those weren't, but then they wanted to be block-structured also. So there are 2 key differences. One is in AMReX, we have a fair bit of generality, so you can have different size grids at different levels. Another thing is that a child grid, which is the finer one, does not have to have a unique parent. So a lot of times when they teach AMR, they'll teach the oct-tree, quad-tree style, because what you do, and we'll show this on the next slide also, is if you have a block of data and there's some point in it you want to refine, you refine that whole thing. So 1 becomes 4, 4 might become 16 if they all refine. But if you tap anywhere in that block, you refine the whole thing. So that gives you a nice pattern there. Here, what we do is we collect a number of cells that we want to refine, and we put a box around them. And it may or not, so you can see that one of the red grids crosses the boundary of 2 blue grids. It's more complicated, but it gives you some nice flexibility. Okay, and this is what I was talking about with patch-based versus oct-tree. Again, names on the left is an AMReX style grid. On the right is this quad-tree, oct-tree. You can loop over things differently because there you know that if you have, for example, if you're going to update grid 7, you know that the grid that was under it, you know that grid 7 itself doesn't cover the coarse grid under it, but you know that the rest of that coarse grid is refined. So you get this quad-tree pattern. Again, both styles break it into logically rectangular packages. We tend to organize by levels. Again, a level is a constant delta x. So delta x equals 1 is a level, delta x equals a half is a level, delta x equals 0.25 is a level. We organize by levels. These tend to loop over leaves on the tree. It turns out that the style of mesh people are used to or like depends a lot on what is the algorithm they had in mind when they did it. This works really, on the right, this works really well if you're doing, for example, compressible fluid flow, explicit algorithms. So you do some operation, you advance everybody at the same time, you go and do go cells. If you're doing something like a linear solve, which there are different ways to do it, there are issues with how you do it. You can do linear solves on the right where I'm talking about solving the Poisson equation, for example. It wasn't really designed for it, so it's more of a reverse fit. So again, one of the takeaways from that is what you choose in terms of your mesh and your algorithm depends a lot on what kind of problem you want to solve. There isn't a unique right answer. Okay, what's an AMR algorithm? You know, a lot of people, okay, I've implemented this cool thing. It works on a single grid. I want to add AMR to it. Well, the bad news is you can't really add AMR. But what you do is you say, okay, I know what to do on one block of data. So key things to know if you have an algorithm, you want to make it adaptive. When I say make it adaptive, first, presumably you already know how are you advancing the solution on one patch of data. Okay. Second thing you have to know is what is true at coarse-fine boundaries. Okay. And before you ask how do you make that true, you have to say what is true. Okay. It depends on the kind of solution, or the kind of system you're solving. If you are doing a hyperbolic system, and imagine you have constant flow. I'm going to use a lot of fluid flow examples. You have a constant fluid flow, and you have some tracer that you're advecting, and it was on the fine grid, and it's moving onto the coarse grid. Well, we know, for example, let's say we're using a flux-based discretization. We know that's a conservative method. So we know that no matter whatever we define those fluxes to be, the amount that leaves one cell is entering another cell. By definition, therefore, it's conservative. So I need that to be true at the coarse-fine interface. Now, if I do an operation on the coarse grid, I compute a flux there. I do an operation on the fine grid, I compute fluxes there. There's no guarantee those are the same. If those aren't the same, I'm going to break conservation. So there's a step I have to take. It's called a reflux step to make sure that I have conservation at my coarse-fine interface. Okay, so what I've just described is what we call a synchronization operation, synchronizing between levels. Refluxing for compressible fluid flow is actually really easy, and it was the first way that AMR was applied. Refluxing for an elliptic problem has an entirely different meaning. You're now a second-order operator, which means now you have a Dirichlet and a Neumann matching conditions. You can't impose those both, so that's a whole other talk. But the point is, if you think about taking a single-level algorithm, making it multi-level, you have to know what you want to be true at the coarse-fine interface. Okay. I've talked a lot about spatial discretization. I haven't talked about time. In the beginning, AMR, again, it was designed for compressible fluid flow. That's how it came to be. In compressible fluid flow, the algorithms they used worked best when the ratio of dt to dx, we have CFL constraint of about 0.9. Okay? What that means is as you add multiple levels, you want to keep that ratio of dt to dx roughly constant. You don't want to be using a so if your finest level is going to determine the dt, when you evolve on the coarse level, you don't want to use that tiny dt, and that had to do with the methods they were using. So they did something called subcycling in time, which means if you have a grid that's a factor of 2 finer, you take a time step that's a factor of 2 finer. Turns out in some cases that's the right answer, and in some cases that's not. So the question in AMR, again, what is an AMR algorithm, you want to design one, you have to decide do you want to subcycle or not. Reasons to subcycle, you take fewer total time steps, and you run at relatively constant CFL. So CFL here in a fluid flow would be velocity times delta t over delta x. You'd like that number to be relatively constant. It also turns out it makes your refluxing or synchronization operations a lot more complicated because now I'm taking 2 fine time steps before I take, I've taken a coarse one, I take 2 fine before I sync. If things get out of whack, it's a little harder to fix them. So people, in the beginning, we were very heavily on the subcycling side. We've kind of swung back a little to the no subcycling because it makes the synchronization easier. Again, no subcycling is same dt on every level. There are also games you can play with the algorithm. If you're subcycling, you have to advance a level completely before you start the finer level. If you're not subcycling, you can break your algorithm. You can say, I'm going to do part of my algorithm on all the levels, and then I'll do something, and then I'll do part of my algorithm on all the levels. So it actually, if you don't subcycle, it gives you more flexibility in your algorithm. At the trade-off of you sort of have to refactor. If you do the subcycling approach, which you can actually do with dt constant, you sort of advance an entire level as if it's the only level there is. You don't think about that. So there are trade-offs. Again, good, bad, you can do what's right for your code. OK, now, Eric, it's all you. So now we're going to try and take some of this, put it into play. You want me to move this out?
Yeah, let's move it out.
OK.
So
In
we're
theory,
going to be starting from that website link that has the hands-on exercise. And while I get everything plugged in and the screen is coming up, why don't you pull up that page so that we'll all be in the same place at the same time.
Yeah, go ahead.
When you do non-subcycling, do you run into stability issues? How do you deal with that?
So you end up with no subcycling. It's usually the finest grid, the finest level that controls the time step. So if you let the coarse grid control it, then you would. You'd have a problem with the fine. The flip side is you let the fine grid control it. I mean, because in almost every algorithm I can think of, smaller dx means smaller dt. But then what that means is at the coarser levels, you're running with a much smaller time step than you need to. And so it's a trade-off. If most of your work's at the fine level anyway, who cares? But if your work's split, then there's an efficiency cost. Yeah. Any other quick questions while Eric's setting up? Yeah, go ahead.
Could you comment on the dynamics of the post-exchange between the interfaces?
Say again, the dynamics of?
Post-exchange.
I'm not hearing, I'm sorry.
Exchange of post cells?
Go cells.
Yeah.
So yes, so we use a paradigm, and most of the things we solve, we use a paradigm where you fill Go cells, people call them halo cells also. You fill those before you do an operation. So if you're going to compute a stencil, a gradient, you might need one Go cell. If you're going to compute a higher order, you might need more. Basically, when you're at a fine level, there are three ways that you might fill a Go cell. One is from the coarse grid, you interpolate. One is from a physical boundary, if you're at a wall or something. And then the third is from other fine grids. So having multiple levels, it adds one additional way of having to fill Go cells. But Go cell filling is a standard operation you need whether you're multi-level or not. It just adds interpolation to the mix of things you might need to do.
So you add the layer of the Go cells like that. You add it to the coarse grid or do you add it to the fine grid?
So every patch has Go cells allocated. So you think about it, every patch, whether it's a coarse patch or a fine patch, the data structure has enough space to fill those. Your algorithm will decide when you need to fill those and from where. OK, and then find me afterwards if that has an answer. OK, Eric.
OK. So what we have on this website is a hands-on activity. And this is really just a chance for you to try out the things we've just been talking about. Obviously, we don't have time to examine every line of source code. But we have some pre-compiled executables for you that you can run to make sure, so you can see that it's actually doing what we say it's doing. So I'm starting from this website. Hopefully, you can see that here, and everybody's in the same place. Thank you for the nods. I appreciate it. At a glance, you can come back and look at this later. But these are kind of the general topics that we'd like you to get out of doing these exercises. So the first thing is a setup. If every single person has been set up, I won't say anything. But so anyways, let me just say a little bit about how I'd like this to go. If you prefer to read, the directions are up here. You can go ahead and kind of work your way through this. For people who this is second nature, you can fly through everything as fast as you want. But for everyone else, if you prefer just to listen to me talk and watch me walk through it, I'm going to walk through the steps now. Okay? So just because we don't want anybody to get stuck on this step, I'm going to start with logging in. I'm doing the SSH-A, just following the directions. It's going to ask me to enter my password. I guess I'm going to just bring this all the way up. And I have to, this is how I do it. I don't know if you've got a better way to do it than me, so.
You've been doing this for 9 days, haven't you?
OK, then we can race to see who's faster. Okay, and then the next thing I want to do is make sure I'm in my home directory. Okay. And then I'm going to copy over the folders out of this directory into my home directory. And because you're going to be using these all day, these are, if you peeked at this website before, there's a general setup directions for all the packages. So this is the way to download all those packages, which may have not been the most time efficient choice. Has anybody already gotten an allocation on Theta GPU? Okay.
Helen thinks you should be good.
Oh, I'm sorry. I should learn how to turn those off. Okay. So I've copied it over. I'm going to move to track 5 numerical, and I'm going to be working in the AMReX directory. The next thing I need to do is get to a Theta.
Just wanted to let you know the spelling of Q self is wrong over there.
Oh, yes.
I got it wrong on the, oh. Put it on the list. Thanks. Okay, so the next thing I need to do is SSH into one of the Theta GPU service nodes. Then the next thing I want to do is verify my, or load the OpenMP module, the one that we want for all the numerical track 5 examples today. So this should be the same for everyone. I think it's, is it 4.1? Yes. Give me all the choices. And I think I want the GCC one. Let me just verify that's what I want. Okay. All right, now I'm going to request an allocation, and this is where we play the waiting game. Okay. How many other people have an allocation now already on a Theta GPU? I see hands.
Oh.
Okay. Okay. How many people are just waiting for an allocation? Yeah. Okay.
Does it matter if we load the OpenMPI before or after the application?
So the advice I was given is the way this one works, the putting you on the Theta GPU puts you on that node. So the answer is it shouldn't. But if you want to be extra safe, better to do it on the node you're going to be running on. Right? Yeah, so the expert advice is do it on the node you're running on. Okay. I got to somehow get rid of that. I should just exit it, sorry. Okay, so this is a good opportunity for you to get ahead of me. The next thing I'm going to do is, what is the next thing I'm going to do? So if you've already on a node, I'm in the AMReX directory. You can source this setup script. And what this does is it's just, it adds a few things to your path. Some other things we're going to use, like FFmpg and ParaView to do our visualization. And it's also just going to check that we have some important parts of our environment set up right. Has anybody gotten through that step already? Yeah, you getting all green? Yeah, okay. Great.
How many people are still waiting for their interactive session to start? I'm going to go talk.
Okay, well, I'm going to kind of pretend I have an interactive session then, and I'm going to keep going down the steps and talking a little bit while I'm waiting. So what we have here is we don't want to just give you code in a vacuum, right? What are we trying to accomplish here? Well, we actually have like a real science goal kind of trying to motivate what we're showing you today. So this is essentially the idea. We have a drop of dye in water, and we have this sort of rotational flow, and we want to see how that dye sort of moves around this object in the water, right? Maybe it's not the most exciting scientific example to start, but it works for demonstrating our purposes today. The point about this example is you don't really care about what happens in the rest of the water, right? You really want to know what's going on with the dye in the water, and specifically that boundary between the dye and the water. So I don't want to spend a lot of computational time way over here in the water on this side of the simulation. I want to focus my computation on that boundary. So that's what makes this kind of a good example for us today. And brings us to our first code, which we're going to call AMR 101. And as the title says, this is just going to demonstrate multi-level scalar advection. So what we're doing here is I have a science problem I want to develop a simulation for in mind. We're going to start simple, right? We're going to get stuff running. We're going to check it. We're going to make sure it's working. And then we're going to add the complexity of the object in the flow later. And even, we might have to update the way we approach it and stuff like that. But that's kind of the idea of what's going on here. Again, details are all here. So if you want to learn more about the mathematics behind the simulation, it's here. And we can talk about that more later. For me, near and dear to my heart is when I start seeing stuff like this. I look at this and say, OK, now I know what's going on. I can imagine the math equations in my head. Right? This is the update on the patch we were talking about. Right? So how do you do your solution on a patch? That's what's going on in this part of the code. Right? One thing just to point out on this part of the code is we have this macro defined here that allows us to write one set of code for both 2 dimensions and 3 dimensions. So at compile time, you can select, OK, I want to run this code as a 2-dimensional code, and this will adjust the source code appropriately. If you decide you want it to run in 3 dimensions, it will make that adjustment as well. Okay. Let me just check. It's still waiting. OK. So this goes back to what do you need for adaptive mesh refinement? We talked about that one patch at a time. We also talked about the coarse-fine boundaries. The reason this part of code is on the hands-on example is just to prove to you that what we're doing is not magic, right? It does involve some work here. So AMReX has a lot of structures in place to support this work, right, for how you're handling a coarse-fine boundary. So in particular, this one, what you're doing is you have a set of data on one level already, and you want to make another level using that data, right? So inside of our AMR core ADV class, we have a virtual function that you have to supply. And the reason why is because we want to be flexible to adapt to all sorts of scientific applications that you want to do, and people do this differently in different situations, right? So again, I'm going to kind of gloss over a lot of details here, but what we're essentially doing is setting up data structures to hold data in a lot of these lines. And then finally, down here, we're calling this function, which is going to take the data from those other levels and use that to fill in our new level. So that's an AMReX function. That's built in there, and that's part of the support that AMReX provides. Right? So my job started. Oh, perfect. OK. And where are we? Right on time for running the code. OK. So I'm just, like I said, I'm going to walk through the steps to run the code. If you're welcome to run the code, if if you're comfortable doing that, please go ahead. So I have to get back to where I was. Sorry, I wanted to make sure my MPI was in the right place. That was what I should have done on the node I was on, right? And I want the GCC version. OK. I'm going to run my environmentals, or I should say source it. Source my script. Everything is good.
Keep going.
OK. Please speak up if you want me to stop or say something again. OK. So again, starting with AMReX 101. Okay, so here I have my precompiled executables, some inputs files, and a script to make the movie for later on. So to run the code, it's going to give me an error. I know this is silly, but this is how I avoid that error. I'm just going to run it with one MPI process first. And so I'm calling my code. I'm going to run it in 3D with MPI support, and I'm giving it this inputs file. Okay. And when I press enter, hopefully everything works. Okay. So I'm going to how much time do you think about?
Oh, they're 5+.
Okay, so what's an inputs file? Just essentially the simulation parameters. We have a maximum time that we want to stop at if we reach that time. If for some reason our time steps are really small, we want our simulation to not just run forever, right? So you can put a maximum number of steps that will stop it also. Things that are interesting for you probably in the short term are the number of cells. That's essentially like the coarsest level resolution, right? And the plot interval that tells you like how often through my simulation I'm going to stop and output that data so that I can generate visualizations and plot files. All right, output my plot files. Okay, but I'll leave it to you to kind of peek in there. The other thing that's interesting is this phi error, because that's determining when you are going to start doing adaptive mesh refinement in which areas and how much refinement you're going to do. So those are the sort of parameters you can use to play with that. Okay, but those are the kind of things that are in the inputs file. So what we want to see is it's running. You can see my time. Total time here is this one in the middle. The steps I'm at. This is the time step I'm taking at each one. And
Why don't you comment on the sum of phi there?
oh, yes. We mentioned, depending on your application, this may or may not be more important to you, but we are conserving the value, the quantity phi. So phi is the value of dye in our water that we're monitoring or that we're simulating that flow in the water with. So in this output is basically showing us that our algorithm is on track to keep that value conserved. Yes?
I don't know if I missed it. Do you say how often you perform AMR? Is it after every iteration or?
Yeah.
Good question.
Yeah, so I mean, we're doing it at each step, right? We're going to check it out and then do our regridding where necessary and simulate on that.
Do you ever pay for that because it's a virtual function? You always have to do a VLOOKUp. Does that really, does that impact your performance at all or not really?
Well, sorry.
Let me take this one.
Yeah.
So as with almost everything in AMReX, the how often you regrid is a runtime parameter. And so in this one, as you said, if it's every time step, then we've just set that to 1. More generally, yes, you'll take a hit with that. And so you typically won't regrid every time step because we think of it, people, if you look at it, you say, the grids are moving. They're not actually moving. When you refine, so you say, I had fine grid here, now I want a fine grid here. What I actually do is create a new grid structure. When I fill it, we saw the fill coarse patch. That was for the first time you create that level. But let's say you've shifted. You used to have a grid here. Now you have a grid here. What you'll do is you'll fill this little part from coarse. You'll copy from fine. And yes, that is, you're interpolating and you're copying. So you usually don't do that. If you have a flow of some sort where things move at most, for example, 1 cell per time step, what you can do is you say, I want to refine this region. I'm going to buffer it a little bit, refine a slightly bigger region, but maybe not regrid, maybe regrid every 2 or every 4 steps. And that's absolutely one of the things that, depending on your algorithm, you have to kind of choose. It's a trade-off. If you make bigger boxes, you don't have to regrid as often, but you're doing more work. So again, algorithm dependent, but good question, yeah. Any other questions while it's running?
Yeah, can we refine on the gradient? Right now, it seems like we're refining on the value of phi. And then you put that, you're refining the gradient is above this.
which is actually really relevant because he said that we care about not where the ink is, but where the ink-water interface is. The answer is with this tutorial, I think it's set up to only be the value, but we do a lot of things. More generally, we usually refine on gradients, not values, depending on, yeah. Yeah?
Do the refinement levels always go in factors of 2, and we have any arbitrary?
Again, a good question. So we typically, for a lot of things, we do 2 or 4, but there's nothing hardwired about that. We're doing a new atmospheric modeling code, and they really like refinement by a factor of 3. As long as my algorithm is written in such a way to understand that, I can do a factor of 3. Yeah.
What about load balancing in that case?
Let's come back to load balancing, because that's a big question.
Okay. So after my simulation runs, I should have generated a certain number, quite a few plot files. In this case, my plot interval is probably too small. But to make a movie out of that so that we can see the simulation result, we've written a script in Python for you. So all you need to do is type batch, pv batch movie, and this is going to use ParaView's sort of Python script built-in thing. And I apologize for this. I could not find a way to make this error message go away, although I tried quite a bit. But I promise you the plot files come out OK. And in the second example, you will not see this error.
And something, you guys had your viz track yesterday, so the AMR plot file format, this is a native format that is written really, it's very efficient in terms of I/O, is read by visit, ParaView, YT, which is a Python. So you can read it out of Python, you can read it in ParaView and visit as a native format, just FYI.
And we're making the movie now, so the movie's good. So I've got the AMR 101 underscore 3D, AVI, and GIF, whichever one you prefer. Do you want to see me download?
Let's keep going. That's something they can look at later.
OK. So after you download this to your computer, what you're going to see is an output like this. So later, if you want to play more of this, you can run this with different MPI processes. Then you can also, one of the key advantages to AMReX is the GPU. So we can take the same source code and compile it to run on GPUs. So if you look in this folder, which you're also going to see here, not that one. What you're also going to see here is another, sorry, this is how I make them all go away. You're going to see another executable here with this one with CUDA. So if you want to see how that one goes, do the same thing. And I can even use the same inputs file and let it run. But yeah, so for you later on, if you want to play with running different MPI processes, see how that affects the time, check our scaling, see if it's scaling well for you. But all that information is in the hands-on on the website, and you can kind of get a feel for what we've been talking about today.
OK, let's take about 2 minutes right now. You can zone out, or you can play with it, and that will be the hands-on for this.
OK.
So 2 minutes, go. While I set up.
I also just want to quickly point out that the source code is with all those examples. So if you are so inclined and you really want to get in to see what's going on under the hood, it's all there for you to check out.
And we go to 10:45, right?
Oh, yeah, that's right.
Yeah,
I was
okay.
thinking 10:30.
No, I've cut you off earlier. Now you see why an hour's so hard.
Yeah.
Yeah.
It's good, though. The questions that come up during the hands-on are helpful.
Yeah, no, that's you did good. Yeah. Just.
Every time you refine, what do you need to reverse back exactly? Because I guess that there's this levels thing for the stencil operations. For instance, if you have a linear solver, it
So
requires the math. You
we done the 2 minutes?
I think so.
Okay, we're going to call that 2 minutes. I don't know if it was or not. We had a question about linear solvers, and so that leads actually really nicely into the next topic, which is, yeah, that was a really simple example. But a couple takeaways from that. One is, so what Erik did ahead of time was made a version that runs pure CPU and a version that runs with GPU. What did he do to do that? He literally, I think he used gmake for this. We have gmake and cmake support. So he went into the new make file and he typed use CUDA equals true instead of use CUDA equals false. So when we talk about performance portability, that's one of the things. The code, if you have written it well, the exact same code in your code will run CUDA, HIP, DPC++. Now, there's a lot of stuff under the hood in AMReX, and the point is you should be thinking, and this is my perspective as a computational scientist, you should be thinking about your algorithm. You should be thinking about the physics, what it needs, how do you discretize it, how do you run it efficiently, what's in your inputs file, how do you initialize your data. In my mind, that's what AMReX enables. You spend your time on that. You don't worry, oh crap, there's a new version of CUDA and something that used to work doesn't, or something. Sometimes AMReX has a workaround because a certain implementation in a compiler is crap. There'll be a workaround. When that compiler version becomes obsolete, we'll take out the workaround and put in something else. So the idea is it's really a division of labor, right? AMReX has people who obsess about those aspects. I personally don't obsess about those aspects. I like to think about the algorithms. So that's what you get. Again, you'll hear this over and over. That's what you get by using a package is there are parts of the overall problem that you focus on. There are parts that other people focus on. So this tutorial wasn't complicated, but again, what did you kind of get for free? If you look at the source code, not that many lines of code. But what you've now got is you've got a code that runs in parallel. It runs multi-level. It does dynamic load balancing. It has visualization support. You kind of got all that for free, in a sense. That's, again, why you use packages. OK, I mentioned particles earlier. It's interesting. When we started the AMReX project, we used to have something called BoxLab. And for those of you who were at Max's talk last night, so Max was a graduate student when we first met him. He was working on this Castro code. This was pre-GPU. He's been a great collaborator in the many years since. But when we first started, everything was about meshes. We were all thinking about meshes. And then people would sort of ask for particles. Hey, can you have like a particle tracer? And oh, sure, we can put in some particle tracers. And then at first, they were just this kind of small class on the side. They've actually become a first-class citizen. I won't say they're more important than meshes, but there are codes like, again, the agent-based models for EPI. That's on my mind because we had a recent proposal, where particles are the dominant data structure. So particles here, and I put it in quotes deliberately, we call them particles. That's the name of the data structure. Okay? So what it is a particle. It has a physical location, and it has a lot of attributes. What it doesn't have is known connectivity to other particles. So particles can be created and destroyed. Now, you can do all kinds of operations with particles. You can find out who are your neighbors. You can find out what particles are in grid cells near you, and then you can find out how many particles of those are within some radius, because those are the ones that you might hit. Again, data layout, there's this AOS versus SOA, which I hadn't heard of 10 years ago. It's array of struct versus struct of array. Basically, the issue is, does every particle carry, if it has XYZ UVW, is the data laid out so that you have particle 1, XYZ UVW, particle 2, XYZ UVW? That's great if you do a lot of work on each particle by itself, but let's say you want to loop over particles and you want everybody's U velocity. Well, now you're having your data access pattern, you're grabbing from every particle. You might prefer to have a 1D array of the U or X velocity, of every particle in that box. So that's the AOS versus SOA. And I always have to think too hard to remember which one's which, so I'm not going to go there. So you have that option, and you can store some of it as AOS, some of it as SOA. You can store reals, ints, things like that. All these tools, things you want to do with particles. Again, you sort of have a concept of ghost cells. Maybe you have a grid here and a grid here. They each own, we think of particles as living on a grid, or a grid as owning particles. So they each own their own particles, but this particle will affect that particle. So you can create ghost particles. You can do neighbor lists. You can do deposition. So in the WarpX code, which was this picture, you see a lot of the one on the left there. There's a lot of operations that have to do with particle information going onto the grid information getting interpolated to the particle. So there's a lot of support for that. Binning, sorting, all these things that you kind of want to do with particles, there's support for. And actually, That WarpX code is a Gordon Bell finalist this year for the particle efficiency. Okay, now we're going to come into our second one because I don't want you to think that AMReX only does scalar advection. So we're kind of adding a few more things. So in the first example, we modeled the dye as sort of a tracer. It was a passive scalar in the fluid. It's not a bad approximation if the density of the dye is comparable to that of water. But let's think of it as a collection of particles now. So you just put a bunch of particles like you're putting some I don't know, powder or something into there. And we also want to make it more interesting. If you remember that first picture that Erik showed, the little movie, there was an obstacle in the flow. First of all, the flow wasn't in a box. It wasn't a square. It was in a cylinder. And there was an obstacle. So let's say we want to do flow around that obstacle. Well, in that first example, we just used an analytic velocity field because I happen to know how to make a flow that goes around like this. But I don't have an analytical expression for the flow around a cylinder. So we're going to compute that. And we want to compute incompressible flow around a cylinder. So if I back up, I have to ask, how do I represent the cylinder? And this comes back to the structured versus unstructured. So in AMReX, as in most structured grid codes, if you want, we can do things like immersed boundary methods. You can add those to AMReX. We have a native support for what we call embedded boundary techniques, which are also called cut cell. They used to be called Cartesian mesh. Those are all the same thing. The idea is an unstructured grid in the upper right, you have these triangles fit naturally against the cylinders, but if you go from the upper right to the middle right, you have to completely redefine your grid. Okay, the difference is in the bottom, and apologize for the graphics, you have a grid, you have particles, you have geometries, solid bodies, whatever. You look at where they intersect, and it's pretty straightforward to ask where that circle intersects the grid. If the circles, if you say, I want to do a different experiment, I want to put the cylinder somewhere else, you lift the cylinder up, you move it, you're not changing the underlying grid. You're recomputing intersections, but it's a much, much quicker process to define these intersections. So again, in the structured mesh, when you create the geometry, you're doing local intersections. In the unstructured, you're having to redo the entire mesh. There are losses of accuracy associated, depending on how high order a method you do. There are high order methods for algorithms, Poisson equation or flow around obstacles. It really depends on how fancy you want to be. Again, don't necessarily use it for boundary layer flow, but for things where, like imagine a stirring of flow, you really want the bulk fluid motion. You don't need overkill. You don't need the exact details there. Okay, so we're going to do an example where we add particles, we add linear solvers, and we add EB as embedded boundary. So we're going to do all three of those things. The fluid velocity is, okay, are we computing on? No, I think the fluid velocity in this case lives on cell centers. We're going to do a Poisson equation, which is going to enforce incompressibility. It's a style called projection method. I think in this case it's a multi-level solve. That's what we call it. And then the passive particles are going to move with the velocity field. And Erik, it should be much quicker because I think everyone knows where to go.
Yep.
So again, if you go back to your AMReX, there should be an AMR 102.
So again, I'm just going to walk you through the steps. Feel free to go ahead of me. So I'm starting again back in the AMReX directory. What I'm looking for is the AMReX underscore AMR 102. And again, like I said, we have the directory where we execute our code, and we also have the source directory, which contains the source code. So if you were curious, you can always go back into there and take a peek. Because I just want to run my code here, I'm going to the exec directory. As before, I've precompiled this with CUDA to run on Theta GPU nodes, and I have one with MPI. So for this example, we're just going to run the code and kind of see how it works and look at the output. So I'm going to use 8 MPI processes. And I forgot to do something important, which was add the inputs file. Okay, so I've called my MPI exec, I've called my executable, I need my inputs file, and this time when I press the button, So that wasn't bad, but to make a more fair comparison, I'm going to run it more similar to the way I did last time, which is I'm going to get rid of my plot files just because it makes things nice, which I believe was one MPI process. And then we will all notice that this is taking a lot longer. Right? And that goes back to the complexity in this example. Right? At each step, we're doing a linear solve to determine what's happening with the flow and what's going on with feed. So every time step, we do a lot more work.
And we should go ahead and show them the movie on the website.
Yep. So I've got my plot files, same thing as before. I'm going to do the pv batch command and call the movie script as so. I press enter. This one shouldn't generate any error messages. And then what you should get is something that looks very similar to this image here. And I'm going to make this a little bit smaller so it fits. Right? And I would encourage you to look closely at this image and verify that the simulation is doing what you want it to do, and ask any questions that come up when you examine these type of things about algorithms and simulations.
And one of the things I want to point out with this one, so two things that we're doing that we didn't really talk about. The red there, I believe, is actually the concentration of particles. So we're doing a particle deposition onto the mesh. So we could, for example, evolve this with particles and then display just the red, which is the concentration of particles, if we didn't want to see each one. The other thing is you look at it and say, that's not a cylinder, that's really chunky. And that's what we call a stair-step approximation. That is a visual artifact that we actually left in on purpose. If you look, there's a shaded cylinder. The problem is this is a 3D thing. We're looking down from the top, and so we moved it slightly. The flow, if you look at the particles, they are actually seeing a cylinder. The reason we left that blue in is because those are cells that are completely covered. And the point of that is no work is being done there. So that's different. An immersed boundary, which some of you may know that, an immersed boundary method does work everywhere and then adds additional forcing terms. In this case, those blue cells, so individual IJKs, are not having any work done. So for example, if you cut out, if you're doing flow inside a cylinder, the corners would not have any work done. Anywhere there is body, like solid in this case, no work is being done. So you don't pay a penalty for having large regions covered by that. OK, should we go back? Yeah. Yeah.
Are those particles just the point particles, or those particles are also mixed inside?
Can you go ahead and undo?
yeah.
I'm going to go ahead and set up while you answer. I apologize. Can you repeat the question? Did you hear?
So I believe the question was, are those particles
Just the point particles, like in the particle cell method, just the point particles going around, or those particles have a grid inside them?
Oh, point particles.
Yeah.
We made them bigger for the visual. They're actually treated as, and that's why they appear to intersect the cylinder, is because we're actually testing on the center of the particle. It's a point particle, does it cross in? If you do them as bigger particles, they look like they're entering. OK, so I just want to kind of wrap up. So AMReX is not the only software package out there. In fact, if you're looking for the tree or octree or quad tree style, there are a number of packages. Flash is an application code that uses it. A lot of people have heard of. It started in astrophysics and has gone into a number of areas. There's packages like pforest, things like that. So there are a lot of AMR packages out there. So if this is something you're interested in, obviously I'm a fan of AMReX. But the things to look at, all AMR packages are going to give you data containers. They're going to manage the levels for you. They're going to manage the metadata. Metadata is where are the boxes, who intersects who. And you might think it's really intersection. Oh, which coarse grid, which fine grid. We cache a lot of the metadata, so we're not recomputing it every time. Regridding is something the package will handle for you. Things will differ. There are packages, for example, that only support cell-centered data. They don't do corner or faces. There are packages that, for example, are only subcycling or only non-subcycling, so things like that. Dual grid means you can decompose the particle and the fluids differently for load balancing. Different kinds of parallelism. Not everybody is GPU ready, and on all three kinds of GPUs. Task iteration support is more detail I won't go into. How flexible is the load balancing? The reason I said load balancing is a huge question because you, as the application person, you know more about what's going on than the computer does. And there are a lot of things that are expensive. The mesh work may be expensive or it may not. The particle work may be expensive. The communication of particles to meshes. if you have an operation that costs the same for every grid cell, then the number of grid cells per box is a good work estimate. It tells you roughly how much that box is going to cost. If you have something like a combustion calculation with chemistry in very localized areas, in the cells where you have reactions, it's very expensive. In the cells where you don't, it's cheap. So total number of cells is not a good work estimate. Basically, you have, I have to take this off. You have to come up with a good work estimate. And you can do that with profiling tools, whatever. But you, as the scientist, have to say, this is the kind of problem I want to write. The answer is different depending on how many particles, how much mesh. Again, additional features. So we have native solvers. We have geometric multigrid solvers. We have a sort of a pseudo AMG solver. Nothing like the ones you're going to hear about this afternoon. And again, how many flavors of GPU? OK, we talked a little bit about this. One of the things that I like, so I grew up on Fortran, and I like array of IJK. We've mimicked that in the C++ style so that literally sometimes you can take a Fortran routine, add semicolons, and be 90% of the way towards having C++ code. Again, we've talked about a bunch of things. We talked about the viz support. Other fun extensions. So in the kinds of things we've talked about, you're doing the same operation at every level, right? We're computing fluxes, we're updating a phi, we're moving it. You can have, if you get creative, you can start saying, you know what? At the coarse level, maybe I'll solve the Navier-Stokes equations. At the finer level, maybe I'll solve something with an additional turbulence model, or maybe I'll change to a particle representation. There are things that you can start to do once you have the flexibility where you don't have to write all this from scratch. Another thing that we're doing is multi-block, where you have two different algorithms next to each other. This is a whole code. This is a whole code. They are solving their equation sets, and then they're talking together at runtime. That's something we do. For example, we're working on stuff for compressible talking to incompressible flow. There are things that you can do where the software framework gives you the tools. You still have to figure out the algorithms, but you have the tools to do it. And as Ulrike was talking about, we don't work in isolation, right? AMReX has multigrid solvers. They're geometric multigrid solvers. They're great for a lot of problems. They're not enough for a lot of problems. So in an AMReX calculation, you can say, I want the hyper solver. As long as you've loaded hyper and you've built it correctly, it's there. You want more sophisticated time stepping. We have we have links to the sundials integrators. I want a different RK3. You can access that through AMReX. We also have something which we're not doing that much now, but we have a code generator that you type something in Python, it writes AMReX C++ code for you. So there are a lot of interoperabilities, and this is a direction we are absolutely going. These codes you shouldn't have to be siloed. Oh, I use this, therefore I can't use all of these. Now, using structured plus unstructured, I'm not sure how that would work, or you could couple them. But things like time integrators, linear solvers, nonlinear solvers, we can absolutely couple with those. OK, this is sort of a takeaway of what you've seen. What's our time?
You're doing great.
OK, that is sort of our takeaway. I think you've just learned that. There is another example, AMReX Pachinko, which you can see. We used to try and include it. We always ran out of time, so we stopped pretending. It shows particles bouncing off of cylinders. And again, there's something where you have no mesh work at all. So what do you load balance? Do you load balance on where the particles are? Well, the expensive thing is really the particles colliding with the cylinders, so do you load balance where the cylinders are? Again, open question. OK, takeaway messages. Let's just see. 2 minutes. OK, takeaway messages. Different problems have different needs, different spatial discretizations, different data structures, different time discretizations. So structured, unstructured, and particles are the most common. AMReX gives you 2 out of 3. Structured mesh does not just equal flow in a box. There are a number of packages out there, but one of the problems, and I'll address this in the wrap-up today, is you don't want to invest in a package and go down this path of building your code in it to get to the point where you say, oh, crap, I can't do this. And I've had that experience in a linear solver. I kept saying, how do you do it? How do you do it? How do you do it? They're like, oh, you can't do that. And I had to completely redirect. So that's an issue. That is a real issue when you use a package. You want to find out enough ahead of time. And it's a combination of two things. One is what is supported now, and the other is what might be supported if you asked for it. That is worth knowing, that the AMReX development team, we're very interested in what people want. And 9 times out of 10, if somebody says, hey, can you do this? And we think it's something that has more applicability than just one project, we will often add it. So it's always worth finding out, is this in your plans? Might this be in your plans? Things like that. And interoperability is important. The rest of today, you're going to learn about packages that play well with each other. Part of the reason that the collection of speakers is here is because we have packages. We want them to play well together. We invest in this. We do testing to make sure that we always can build with Hyper. There's a lot going on. Erik can actually talk a lot more about CI testing. We do a lot of CI testing. We're trying to make sure we can build on all the machines, that we can build with all the other software versions. OK, and finally, just a fun takeaway. This is your gratuitous sales pitch at the end. Thank you.